Hello all, welcome to my channel. Uh, I'm back with a new video. In this video, we will be seeing how we can debug a memory leak that happens in a Spark application. This is a real time, not real time, this is a real life scenario which I faced while doing a migration. And we will see what are the steps and how we reached and fixed this issue um, in Spark. So let's get started. So, the things that we were working on this was within a migration application. Our jobs were running fine on HDP, which is Hortonworks Data Platforms 2.3, and it was then upgraded to Spark 3.2 on Yarn. So that's what the migration happened. So we upgraded the clusters to 3 2.3 to 3.2 on Yarn, and the job which was running on 2.3, initially the test job which we ran after the migration was over, which ran fine, and after sometimes uh, when the actual job was processing the real data, at that time it threw an error, and the error, this job had retried set to 4, so it again tried 4 times and then it failed completely. The job owners then got notified, and he let us know that okay, after the migration we are seeing this issue. So so how things work is that the way the moment we received this notification that okay, the job is failing after the migration, so when we started to look at the logs, and what I observed was there were too many errors with messages like error course gained executor backend received signal termination. So this error was persistent across the logs, and this happens when we have executor being removed while running with dynamic allocation. So to let the job, what did was I asked the user to run the job with increased idle timeout, and it was increased to 900 seconds. And after this running this job for certain times, we did not progress much, but the error message changed in the log file. It was now flooded with a different message which used to say that okay, executor heartbeat timed out after X milliseconds. This error meant that the executor was not able to communicate with the driver in the stipulated time, which is the default time that we have set. Uh, so while we were still debugging further that we how we can run this job with higher timeouts or not, uh, we tried out. We ran the job with an higher heartbeat, and then we saw the following application which says the driver terminated or disconnected. This error message, when you see application master aim in point driver terminated or disconnected, this line simply means that the driver is gone. And so to find out why the driver went away, we looked at the driver log, and then we found out that java.lang.out of memory GC overhead limit exceeded. So we figured out that okay, there is a GC pause or GC overhead limit error is coming. It was evident that driver is having a memory processor. So I asked to increase the driver memory from 28 GB to 40 GB, which would have made it and also added an overhead from 6, which was earlier for 6 GB, then we increased it to 12 GB, and reduced the number of cores, which was earlier 10 to 4, which uh, uh, we were looking at things, and then we saw that okay, this job still got still got killed. So next time when I ran the job in the client mode with 60 GB of memory for the driver, the job finished few of the stages that were failing earlier, but it failed soon after that. So we when the ran job it's 160 GB of driver memory, then the job succeeded. So that's when we came to know there is some kind of a memory leak that is happening, that this job which used to run fine with 28 GB and 6 GB of overhead now is taking more than 160 GB of data, 160 GB of memory. So, but again, 160 GB of driver memory we can't provide to this driver because we have, as a cluster which is multi-tenant, we enforce a hard limit of 32 gigs in the cluster mode. So we started to look out for the reason why the driver is consuming so much of memory. So we enabled Java heap dump after the for the driver, and we added some new parameters like it was 3.2, so we started to use G1 GC. We enabled heap dump on out of memory errors. We also added to use the compressed objects, provided the heap dump path, print flag. So we added some diagnostics VM options as well. And we also enabled the debug mode to true. Also, we added verbose for the GC. So whenever the GC will happen, it will give the full verbose output. So after looking at the heap dump, so to analyze the heap dump, we just onboarded this into Visual VM, which is to visualize the virtual memory object or JVM objects of Java. We use Visual VM. So Visual VM is the tool that we used. We imported this, and then when we started to see the heap dump overview, we noticed a few things. One was that the biggest heap dump overview, it said it used a 59 GB of heap dump. Number of objects were almost around a billion. Number of classes were 26,000 almost. So we looked at these things, and then what we did is we also looked at this uh, map which says which object, the biggest object size and everything. So around 36.3 GB were of this class, which is called scala.collection.mutable.hash entry, which we were thinking that something which should not have happened, but it was there. And so this is the second highest was the Scala collection parallel and part parallel iterable like map. That class object was there. So to find out why these two classes are coming up so frequently in the heap dump, we looked at the code, and the code was like this. So which says variable. This is not the actual code. This is the slightly what you call change code. So in this, what they were doing is they were looking at a path. If it was on a directory or a file, based on that they were taking certain decision. And for files, so files dot parallel dot for each, they were making a call. They were getting the file name. They were converting to a string. Then they were reading the file using that get path of JSON. So it was a JSON object, and then they were doing a file map update, the file name and the data frame that was generated. The above code is reading, again, simply meant is above code was just doing a JSON file read one by one and keeps a map of the file names and corresponding data frame. So this is what it were doing in the file map. We were keeping the file name and the corresponding data frame. Ideally, this should just keep the references to the data frame, because data frame is something which should be distributed, not to should go to the driver. But the GC showed otherwise. In just 10 minutes after reading the files, the memory footprint shot up to 60 GB and kept on increasing. So we decided to change the code so that instead of reading it one by one, we will read it in one go using one spark read.json instead of calling the spark read file for each file along with the file name. So what we did is we used a function. So in Spark there is a function which we can use to get the file names for each of the rows which are there. So what we called is call UDF, which is get file name, and we pass the input file name function. And that way we added a column where each of the record had a file name associated with it. And also we changed the files for parallel for each, which was happening in thread pool. So sorry, it was not happening with thread pool earlier. So we created a fork, we created a uh, task, and then we added those to use the fork. So after doing these things, we started to see that yes, the process was running fine, and we were able to get the process to run with 32 GB memory itself. There was no uh, extra thing that we have to do further. Uh, so to give an idea of why G1GC settings are important, like why we decide on this one. So for example, what is the initial heap? What is the concurrent GC threads, parallel GC threads, new to young ratio, and region size. So these are the few things which are available with the G1GC Venpa. And after the code changes, the job work with 30 GB memory itself. The interesting thing to note here is this I will not talk much about, because this is something which is common. Like if you are Java developer, you will see how G1GC works. Uh, the thing that was interesting is that we found out later on that this issue, which the same job which was running fine in 3.3 and started to fail in 3.2. was because of the change that was done. So Scala versions was changed from 2.11 to 2.12.15, and something with the Scala version itself was causing these memory leaks. So we found out, we notified this to Spark community, and they also acknowledged that yes, this is a change. This code which was working fine earlier will fail in because of the way 2.12 happens handles parallel and for each classes. So how do we check the heap dump? So we can do the SSH into the Spark submit from where the Spark submit was run. Get the process ID of the Java process running on the top. Get the heap dump like jmap dump. You provide the file, and then correct permission, change the permission to 444 of that output file, and then use any convenient like visualize or summarize of heap dump, and then you will get something like this. And then you can this gives a drill down as well. You can click expand and then go down. Apart from Jmap, there are other tools like JStat, JHat to analyze JVM. For example, JStack simply takes the link, it links with the PID, and then it will threaddump.pid is the file that we can create. So the summary of how we debug is that check the executor logs, check the driver logs, check the GC activity, take the heap dump of the driver process, analyze the heap dump, find the object that is leaking the memory, fix that memory leak, and continue again and again till you have the solution. So yeah, this was a very good work. It's very interesting work to find out why certain things do work and certain things don't work in a given environment. So hope this helps. And if you have any interesting uh, situation where you had to debug and find the memory leak and why it was happening, do let me know in the comment and how you were able to fix it. So this so that others also in the community can get benefited from this. So yeah, that's it for this video. Have a nice day.